One of this form real quick. Well, and this guy, all right, let me see. If I have something approaching 1, but it never gets to 1, and I'm raising it to a power that's getting bigger and bigger and bigger, how we do so far? Then it's not necessarily going to come out to be 1 at the end. It's never, the base is never 1 necessarily. The limit is 1. Right? So if you did 1.1 to the 1 trillionth power, it's going to be huge. And if you do 1.00001 to the trillion to the trillion to the trillion power, it's going to be huge. If the base is not exactly 1 and you raise it to a very large power, the result can be very large. Right? So this could be, if this is going to 1 fast enough, then it's going to come out to some finite number. If this is going to infinity too fast, then it's going to be infinity. So it's all about, do they even out, or does one beat the other one or something? Same thing as always. Right? So, let me see. Let me get a good example of that second dude.
What do you mean by going to 1 fast enough?
Here, we'll do a problem. That's all this is about, right? Like the problem we just did, it was going to infinity. Which one's going to infinity faster? So was the bottom going to infinity fast enough to dampen him down? No, it couldn't keep him in control. This guy's just growing way too fast. That wasn't growing fast enough. So he won, so the whole thing went to infinity.
So the indeterminate forms that you wrote down here, you're assuming that those are limits. As the limit
Yeah, exactly.
Okay.
Indeterminate form, that expression relates to limits.
Okay,
Yeah, good. Not just something sitting there.
Like,
If you saw 1 infinity sitting somewhere, then you wonder about who wrote that. But this is a form. These are forms that... Yeah. Because you're not allowed to write infinity inside of something. You're just not. You're just saying what form it's in. Okay. Let me get one that's... Oh, here we go. Perfect. See how you feel about this. Ooh, I like it. I like it more than I should. So what form is this in? As x goes to 0, what does the inside do? Goes to 1. Right? In fact, I'll even say it goes from the bottom. So the inside goes to 1. And what's this do? Yeah, because cotangent is cosine over sine, and sine of 0 is 0. So that's going to infinity. I like it. So it's in the form 1 to the infinity. All right, so let me see if somebody has a suggestion as to how to handle this. Remember when we did derivatives of stuff like x to the x? What did we have to use? Logarithms. We had to do logarithms to help us out. We're like, freaking hell, there's a function and a power. We need something that can bring that down. Right? So you say, this is what you're working with. So what's the natural log of that? Cotangent x. Got it, 4. Right? So you apply the limit to this, and whatever answer you get, you have to raise e to it to get y back. We're not doing derivatives. You understand? We're not going to do 1 over y times y prime. We're not taking derivatives. We're applying a limit. So whatever the answer I get to this is, I've got to raise it e to it to kill this ln. The answer I'm going to get is going to be the ln of what I want. So the next step to realize is, what form is that in now? So if I do the limit, this x goes to 0. Good. So this is 0 times infinity still, right? Just like it was before. It was infinity before. You guys still with me a little bit? So therefore, it's not. Is it in the form that I can use L'Hopital's? What does L'Hopital's rule work on? Ratios. L'Hopital's rule only works on ratios, but I can make this, so this is currently infinity times 0. I gave something away earlier when I said something about what it was going to infinity. I just can take one of them and reciprocate. So actually the cotangent is just reciprocate it and you get tangent, right? But it still won't be a ratio, so you got to be careful. So you want to write it as limit x goes to 0, natural log over tangent. I love it. So now what form is it in?
It's in a ratio.
0 over 0. I like it. So now it's in a form that L'Hopital's can handle. So now you apply L'Hopital's. It's great. So now this is in 0 over 0 form. So how do you take the derivative of the top? Yeah, 1 over 1 plus sine 4x times 4 cosine 4. I like it for the chain rule inside the 4x, right? 4 cosine 4x over secant squared. Yeah, cool. I like it. Oh, yeah. Right? So now you just investigate where you are now. You kind of simplify that a little bit. Can't I bring that 1 plus sine 4x down? Is that cool? So I can at least do that. Where am I at?
No. Bring it down.
Yeah, 4 cosine 4x over secant squared x 1 plus sine 4x. So that's where we are now. Is it still indeterminate? When you plug a 0 in, what do you get here? Cosine of 0 is
1.
1. So it's not indeterminate. So let's start to do it. We don't want to. We can't apply L'Hopital's rule anymore, right? So this the top then, like John said, is 4. 4 times 1. Kick ass. Secant squared of 0 is 1, right? Because that's cosine basically.
Yeah,
Cosine is 1. 1 over 1 is 1. Squared is still 1. It's crazy.
That's what I was like.
And then
0.
sine of 0 is 0. So you're just left with that one. So it is 4. Cool. So is that the answer? That's what y is. That's what ln of y is. So what's the actual answer? What's the limit that I need? So y is the limit as x was 0 of the original problem. Got there. So that is equal to e to the 4th. I like it. You got to kill that ln we had to bring in, right? So before we used it, we had to use implicit differentiation when we did it because it was all about taking derivatives. This is all about taking limits. Now that we know L'Hopital's rule, we're like, oh, derivatives help us take limits, but I'm still just taking limits, so there's no implicit stuff here. I just, whatever answer I end up with, I got to do e to it, and that's the actual answer to the question. Because I got to kill that ln that I had to do there. All right. So that's one freaky thing that could happen. I think that's all the time I got. Shit. So we still have to talk about infinity minus infinity. We just did 1 to the infinity. And real quick, guys. Somebody tell me, well, let's see if this makes sense, what that limit would be?
0.
Yeah, why? It's 0, exactly. So that's related to why this is not an indeterminate form. The minute that the base is below 1, it's going to go to 0. So this is not indeterminate. I don't care how slowly I'm going to 0, at some point I'm less than 1. And then it's just going to go to 0. It's got no chance. The minute the base is less than 1, it's going to go to 0. Good. I like it. That's why that's not indeterminate. All right.
Sorry, answer that.
Oh, guys, you probably want the practice test. Oh, good. I have so many of them left over.
So e to the 4th, is that that's like a relationship between how fast and how going. 1 is going to 1 and infinity is going to infinity. This is a number, right? E to the 4th.
So the result is kind of related to the differences in the speeds at which they're going to the respective things, but you can't say it's equal to it or something, but it is related. So the smaller this is, the quicker, where am I at here? So this is more and more closer to 1, the quicker this was going to 1. The bigger this is, the quicker this was going to infinity.
Okay.
Does that make sense?
Yes.
So it's not an exact measurement, but it is you can tell who is going quicker based on if it's closer to 1 or if it's closer to infinity.
That's pretty small, right? Each port's like 3 to 4.
Relatively, yeah.
Yeah.
Because it could be anything up to infinity.
Yeah, right.
But that
Yeah.
scale it's not a linear scale exactly. So that's why you can't say.
Just do the math. Don't worry about it.
Yeah, exactly.
Okay.
Yes.
Can I grab one of these?
Yeah. Which one is that? That's the one we're doing. Yeah.
Yeah.
Cool.
Thank you.
Sure.
Nice. Get your practice hands. These.
Thanks, John. Thanks, Ken.
Three.
I like it.
I got one of these.
Yeah.
When is the test, by the way? Tomorrow
Wednesday.
or Wednesday?
Tomorrow.
Tomorrow you're on class, right? Yeah.
No class tomorrow.